Hi, my name's Lucas Hawley. I'm a senior biomedical engineer. I'm the team lead.
Hi, I'm Connor Ngor. I'm a mechanical engineer major and I'm the procurement lead for this project.
Hi, I'm Joe Leong and I'm a senior in electrical and computer science.
Hello, my name is Riyad Sohail and I'm a mechanical engineer.
I'm Max Critchfield and I'm an optical sciences and engineering major.
A quick overview of the Adaptive Robot Gripper project. The Adaptive Robot Gripper is an automatic system for manufacturing arms to adapt to the changes in the types of products coming down the line. The system collects location data, identifies the object, picks up the product, and transfers the product to the drop zone. Problem description. Unilever operates over 300 factories across 69 countries with over 400 brands to deal with, requiring a constant mix of products that need to be handled by the manufacturing line. Unilever currently stops the lines and manually replaces the gripper to fit the products. That's where we come in.
The objective of the Adaptive Robot Gripper project is to produce a viable prototype that can operate in an industrial setting. The ARG system will have the ability to adapt to different products coming down the manufacturing line by having the ability to independently tell what product is heading towards the gripper, identify where the product is on the conveyor belt, and adjust its orientation and grip force to grab the product for transportation by the robot arm without damaging or leaving a mark. The ARG system will be comprised of a camera system, a gripper, and emulation software. The camera system will identify the product and find its location on the assembly line. Geometry of the recognized item will be retrieved from stored data in the Raspberry Pi. This information will be sent to the arm and gripper so the product is handled carefully. The software for this project will allow the recognition system to send the appropriate information of each identified item to the gripper and robot arm. This allows the gripper and robot arm to properly respond to each product so that they are carefully handled and damage is avoided. The included emulation software will simulate the manufacturing environment, industrial robot arm, gripper, and products on the conveyor belt. The emulation software can generate a Python code that creates coordinates to guide the robot arm to pick up and drop each product.
In our point design, we decided between three concepts, including vacuum grippers, soft grippers, and hard mechanical grippers. In our evaluation, we chose to go with a hard mechanical gripper to best conform around the rigid products. Mechanical grippers are more flexible, adaptive, and inexpensive. We chose the mechanical approach because of the information available to us, our expertise, and we knew it will be the best option to work with and optimize. By prototyping our gripper, we realized and knew the exact right size and weight to grip our objects and adapt around them. We also realized to add some parts to better grip and safely drop.
To verify the Adaptive Robot Gripper system, we received several requirements from our sponsor Unilever UK. The major of these requirements that informed and guided our decisions included that the ARG system be inexpensive, the system must not exceed the original $4,000 budget of the design competition, the system must be able to recognize objects traveling down the manufacturing line with near 100% accuracy, the ARG system must be able to tell the distance of a stopped object to within 5 millimeters, the cycle time of the system must be below 2 seconds for a pick rate of 30 picks per minute minimum. The Adaptive Robot Gripper shall be able to grip all 5 given example products, and requirement to include an emulation software package to replace the physical robot arm.
First, the ultrasonic range sensor repeatedly emits sound waves to determine whether an object is on the conveyor belt. When the range sensor returns a value within the range of the conveyor belt, the camera then takes a picture of the object and uses the trained neural network to identify the product. If the product is successfully identified, the gripper will then use the correct step resolution and step count to securely grasp the product without crushing it. The gripper uses a single stepper motor to drive the 2 fingers, which are padded with plastic, for additional grip resistance. The force resistor lays between the finger and the plastic and senses whether the gripper is applying force to the product. Lastly, after moving the product, the gripper will return to its initial position, ready for a new cycle. Since we do not have access to a robot arm, the RoboDK software will act as a stand-in and emulate all the actions.
The two major subsystems we tested for the ARG are the visualization system and the mechanical design and motor control. The visualization system consists of a camera and an ultrasonic sensor attached to a Raspberry Pi, which processes the data they collect. We loaded the image recognition software, YOLO V5, with over 1,000 test images of Unilever objects, and then tested the ability of the camera and the Pi to correctly identify each of them. The image recognition software uses bounding boxes to identify the object, then gives a confidence value in its selection. From our test images, we found that any image with a 70% confidence or better is certain to correctly identify the object. By putting various objects in front of our camera and confirming they are correctly identified with 70+% confidence, we were able to certify our system's ability to identify the objects accurately. The other component in the visualization system is an ultrasonic sensor. The sensor uses sound waves to identify distance, which is useful for determining an object's position on the conveyor belt. For this test, we compared physical measurements of the output of the sensor and confirmed that they were always within 5 millimeters of each other. This was the case for all of our trials, so we were confident that the measured distances will be accurate. The gripper itself and the motor controlling it is the other major component of our system. It has a force sensor on one of the fingers to monitor whether it's holding an object or not. We were able to verify the grip force from the motor is large enough to trigger the sensor. Another substantial requirement is that we can pick 30 objects per minute. Since we did not have access to a robot arm, some analysis was required for this step. 30 picks per minute equates to 1 pick every 2 seconds. We were able to open and close our gripper within half a second, leaving 1.5 seconds for a robot arm to move the object and then return to the pickup point. As can be seen in our emulation, this is plenty of time for most industry-standard robot arms. Following our test results, we can look back and see how well they meet our functional requirements. The RoboDK emulation shows how our gripper would function in an industrial environment as well as its appropriate timing. It can pick up varying objects, and while we have designed an interface plate that can be used to connect to robot arms, we've replaced it with a handle that is better suited for our demonstration. Finally, the ARG is capable of operating without a human operator, assuming it were attached to a robot.
The deliverables to Unilever include our final report, including TDP, SRVM, verification documents, STD, source code, and our software manual. Also included as part of our deliverables are our prototypes, including all plastic and metal prototypes, as well as the software through a GitHub file.
In senior design and in industry, it's important to communicate with the vital stakeholders of the project to ensure successful development and delivery of the project.
One of the important things I've learned about senior design was to keep proper documentation of all our software so it can be readily accessible and also updated.
I'd say the biggest thing I learned in senior design was time management. Even though a task seems like pretty small or quick, it's best to get it done early because you never know when something else is going to pop up or when other delays will come into it. So it's best to be prepared and get things done quickly.
One of the biggest takeaways from senior design was the importance of testing. No matter how much you plan and how much you design, you need to test early so you can find out the mistakes early.
One of the biggest takeaways that I got out of senior design was redundancy. And so what this is making sure that you have extra parts and extra pieces and motors just in case one of those fails or breaks. We always have a backup.
Safety and environmental concerns. The ARG system is to be eventually deployed in the factory setting along with robot arms to pick and place various objects off of the conveyor belts. The GUI is equipped with an emergency quit function to send instructions to release the gripper before shutting down the program. At this time, we'd like to thank Unilever UK for sponsoring this project and their constant communication and help from the other side of the world throughout this project. Special thanks to Dr. Slepian for connecting with Unilever UK, Don McDonald, our professor, for his support of our project outside of the class periods, Dr. Enkoff for opening lab space for us, and major contributions to the motor control portion of our project. Thank you for watching.